Hi, I'm Leon Starr, and this is Lesson 230, Executable Relationships, in my course, How to Specify Software in Complex Safety Critical Systems. Up until this point, we've limited our focus to individual platform-independent classes. But most of the fun and pain happens when we model relationships among these classes. That's because relationships model precise expressions of logic in our requirements. Many modeling methodologies play fast and loose with relationship definition, just drawing lines with vacuous role names. But not us. Just as we do for classes, we use an executable definition for relationships, so we can test our work and fail as we go along. In fact, our whole philosophy is to fail early, exposing logical contradictions and ambiguity in our requirements and just a plain lack of information. The sooner we know what we don't know, the better.
It's always a good idea to look at least one actual scenario before we try to abstract anything into a model. Here we have some aircraft queuing up for takeoff. Actually, the one there on the right is taking off right now. And each of these jets is an instance of our aircraft class modeled in Video 210. An outbound aircraft must be assigned some runway for takeoff, and, for obvious safety reasons, this is always done prior to takeoff. Please note that this rule is a real-world policy and has nothing to do with writing code. We didn't design this rule, we observed it. Let's model this as a relationship between our aircraft class and a newly defined runway class. We abstract a relationship by considering the meaning and multiplicity from the perspective of each class. Let's start with an arbitrary aircraft. From its perspective, a single runway is assigned for takeoff. This perspective has a 2-1 multiplicity. Flipping it around, we see our runway's point of view. At a given time, a runway may be assigned to multiple aircraft for takeoff, so the multiplicity is too many. We can visualize the runway assignments in our scenario as a mapping between elements of two sets. Aircraft are identified by their call signs and a runway by its name, 33L in this case. Taking the aircraft's perspective, we illustrate the many-to-one mapping. Then, from the runway's perspective, on the same relationship, we see the one-to-many mapping. Since we are observing a single relationship, the mapped instances are the same regardless of perspective. The lines help us visualize the mapping, but what we really need is an executable representation of this data, so let's bring up our class tables. Let's first take a look at our two class-based tables, aircraft and runway. We presume there are multiple attributes in both of these classes, like heading for aircraft and maybe length for runway, among others, but we'll focus on just the identifying attributes for now. So how do we capture the fact that our three aircraft instances are each associated with a single runway? One way is to create a third table where we create a row for each mapping. This table correlates the call signs and runway names with a column for each identifying attribute. Each row then represents an assignment of a runway to an aircraft. Each value in the call sign column must match a value in the referenced aircraft column, and each runway value must match a value referenced in the runway table. Consequently, we call each such attribute in our correlation table a referential attribute. Now let's think about what each row in this third table represents. Each row is in fact an instance of a takeoff assignment. Hey, did this third table just discover a new class? Like takeoff assignment? It might even have some additional attributes. The time of the assignment, for example. If so, let's rename the referential attributes to aircraft and runway so that the class makes a bit more sense. It's okay to rename a referential attribute as long as the data type of that attribute matches the type of the attribute you are referencing. Now, you might be uncomfortable with the non-physical nature of this proposed class. Whereas both aircraft and runway are things you can go out and kick, a takeoff assignment is a policy. But physicality was never part of our class definition if you go back and watch Video 210 on classification. There we define a class as a set of real-world entities with common attributes, common behavior, all subject to the same rules and constraints. Here, we're saying that takeoff assignment entities meet that criteria. And, as with any class, if it does turn out that any of the instances require special treatment, we'll have to rethink things. As we'll see in later videos, physical entities are just one of several possible kinds of real-world classifications. As promised, we're going to test these tables to make sure we haven't done anything stupid. But let's first add back all the non-identifying attributes and take a look at how a relationship is drawn in our class diagram notation. Each of our three tables is drawn here with UML class rectangles. Here we see the class and attribute names as well as the attribute types in separate compartments. We draw a solid line to represent the association between the aircraft and runway classes, and we draw a dashed line to show that each instance of takeoff assignment is actually the result of associating an instance of runway to an instance of aircraft. We call this an associative relationship, with one class playing the association class role and the other two in the participating class roles. Now let's place the perspectives and multiplicities on the relationship. Aircraft has been assigned to take off from one runway. But let's think about that for a minute. In our scenario, each aircraft was assigned to a runway for takeoff.
But would it be possible for an aircraft to not be assigned to any runway?
It seems like the answer should be yes, since some outbound aircraft might not be waiting for an assignment. So we'll make the multiplicities 0 or 1 like so. The UML notation means 0 to 1, which is effectively 0 or 1. Let's hide this for a minute and go to the other direction, taking an arbitrary runway's perspective. A runway has been assigned for takeoff to many aircraft. Could a runway exist that has not yet been assigned? Well, sure. There are a whole variety of reasons why a runway might be unassigned at any given moment. Maybe there are no flights ready to take off. Maybe the runway is facing downwind at the moment. So we'll mark this as 0 rather than 1 to many. Pause for a second and consider how thinking about the 0 case in our multiplicity forced us to consider cases outside of our observed scenario. Of course, we might have reached the same result if we had studied more than one scenario, but even then, we might not have encountered all possibilities. We call the 0 or 1 decision conditionality, and I can tell you from experience that this is one of the best ways to detect edge cases as we model. It will be useful to have a short name to refer to the relationship as a whole, and we just use the letter R for relationship followed by a number. We'll call this R1 for no particular reason. Take a look at the referential attributes in takeoff assignment. We tag these so that we can see which relationship they are referencing, R1 in our case. Because the same aircraft cannot be assigned more than one runway, it can appear at most once as a takeoff assignment. So the aircraft attribute serves as the identifier of takeoff assignment. You may want to go back and take a look at the populated tables to see why the same runway value could appear in multiple instances and is therefore not tagged as an identifier attribute. Next, we're going to add some more instances to our scenario so that we can have examples of the conditional cases. I'm going to show these using the set representation with just the identifier attributes so that you can easily visualize the mapped and unmapped instances. One way to test our tables is to see what questions they can and cannot answer. So let's try this one. Are there any aircraft assigned to runway 33R? Can our tables answer that question? The answer is yes. They can answer that question. Can you see how? Right, we just checked the takeoff assignment table, and since 33R does not appear, we know that no aircraft has been assigned to it. Let's try another. How long is the runway assigned to aircraft TK2103? Can our tables answer that question? If so, how? Well, yes they do. We consult the takeoff assignment table to find TK2103 and see that it has 33L assigned. Then we can see that 33L is 305 meters long in the runway table. Okay, last one. Is runway 33R long enough for UA 128? What do you think? See, here's one the tables do not answer. Nothing in these tables tells us the takeoff requirements for any given aircraft or model of aircraft. Is that a problem? Well, it depends entirely on your requirements. Perhaps our system will be designed to trust the air traffic controllers to know and accept whatever assignment they make. It will certainly take us less time and effort to specify such a system. Alternatively, we require our system to validate the input, in which case we would need to do a bit more modeling. Once we've learned some more modeling techniques in later videos, we can revisit this exercise to see how it could be done. If you think about it, we didn't really need to put any data in these tables to evaluate our questions.
Let's go back to our class diagram. Notice the big difference between the diagram and our populated tables. When we fill the tables in, they represent a specific scenario with specific instances. But the diagram doesn't tell us anything about any particular population. Look at this thing. Our diagram gives us an abstraction that applies to all possible populations. So when we say on relationship R1 that any given aircraft has been assigned to take off from 0 or 1 runway, well, actually that sounds a bit awkward since we know that 0, 1 actually means is or isn't. So typically we would read a conditional 1 multiplicity like this. Any given aircraft has or has not been assigned to take off from a runway. And notice that we cover the part closest to the source class and read the verb phrase on the opposite side. This perspective states a rule that applies to any possible instance of aircraft. And we abstracted the class aircraft on the principle that each instance follows the same rules. So R1 applies systematically to all instances of aircraft and runway with no exceptions. And if you can think of some exception, then the model is wrong and we need to modify it somehow. Because that's the whole point of the model. It boldly states the logic that applies universally in our system. This stands in contrast to weaker, non-executable approaches to modeling where you can hand-wave and qualify your way out of the logic only to find the trouble during implementation. Here you make concrete statements that can and frequently are proven wrong. We'll only be able to achieve certainty by carefully abstracting our classes and honing our relationship phrases, multiplicities, and conditionalities. And that skill is a lot more difficult than what may appear to be a trivial task of drawing boxes and lines, especially as we expand our scope to more interesting problems. So that's a whirlwind introduction to our most fundamental kind of relationship, the associative relationship. We glossed over a lot here, but don't worry, we'll cover the various relationship types each in their own in-depth videos. The important thing is that we observe relationships among the entities in the world of our system. An associative relationship has two perspectives. For each perspective, we describe it with the verb phrase and determine its multiplicity, one or many, and the conditionality, whether or not 0 is an option. We make the relationship executable through the use of referential attributes. A referential attribute holds a value of an identifying attribute on one of the perspectives and has the same data type as the referenced attribute. And most important, we make decisive statements about the world of our system that we will repeatedly test as we develop our models. How exactly do we model all these different types of relationships? More importantly, how do we combine them to express complex requirements? We're going to cover that, and I've got all kinds of great examples to play with. But first, we need to get clear on what kinds of things in our system's world can and cannot be classes. Good classes are going to set us up for success. But there are some seductive, evil classes that will put you on the road to box-in-box modeling. No worries, I'll help you out with that in lesson 240.